Okay, let's talk a little bit about charge. Charge is indicated by a letter Q, a capital Q or little q, and usually a big Q means a large charge and a little q means a small charge, but you can use a big Q or a small charge to a big Q or a small q to mean charge. So they mean charge, and the units of charge, the MKS units of charge, is the Coulomb. Charge is the Coulomb, or capital C. Now there is a fundamental unit of charge, and the fundamental unit of charge is the charge of the electron or the proton. Now remember, in an atom, so this is not the Earth anymore, it is now an atom. In an atom, you have the nucleus, and in the nucleus, you typically have plus charges and neutral charges. They're called protons and neutrons. And then around the nucleus, you've got electrons, which is usually the E minus, indicating that it's a negative charge. So in the nucleus, you got protons and neutrons, and then going around the nucleus, let's get rid of that picture there, we've got the electrons. At least in a classical atom, it's floating around that nucleus somehow. And in a neutral atom, which is your sort of typical small atom, might be neutral, might not be, but we've got the same number of protons and neutrons. So what I have drawn here with one proton, one neutron, one electron. Did I say same number of protons, neutrons, and electrons? With one proton, one neutron, one electron, this is a hydrogen atom. If I add a second proton, a second neutron, and then we don't have to have a second electron, but we might have a second electron, that's a helium atom. We add a third proton, third neutron, third electron, it's a neutral lithium atom, etc. So these protons and electrons are the fundamental units of charge. Fundamental means you can't get any smaller. Now that's a lie, but only a little bit of a lie, because these are the stable charges. You can actually break a proton up into quarks. I'm sure you've heard of quarks. You can break neutrons up into quarks, and quarks are charged particles. A neutron, which is neutral, actually has an even number of positively charged quarks and negatively charged quarks, or the same number of positively charged quarks and negatively charged quarks, while the proton has a net positive charge because it's got more positively charged quarks than negatively charged quarks. But for the sake of the kind of physics we're doing, we're only going to think of protons and electrons as the fundamental charge, because quarks are not stable by themselves. They have to come, if we find them separate from things, it's because we've blown something up. So the stable fundamental charge is the electron or the proton. And the charge of the proton is plus 1.6 times 10 to the minus 19th coulombs. This is given the fundamental charge letter of E. And so the charge of the electron is minus 1.6 times 10 to the minus 19th coulombs. And so that's given the fundamental charge of minus E. So don't get confused between this E minus thing that indicates the charge that indicates an electron versus the fundamental unit of charge E. In any case, you won't let yourself get confused. If you're thinking fundamental charges, we know that the fundamental unit of charge is plus 1.6 times 10 to the minus 19th coulombs. And if it's a negative charge, it's negative 1.6 times 10 to the minus 19th coulombs. So we should know from the context whether we put a plus or a minus sign in there. So what I want to point out is that 1.6 times 10 to the minus 19th coulombs is a very small charge compared to 1 coulomb, compared to the MKS unit. So a coulomb is a lot of charges. How many charges in coulomb? If I have a coulomb of charge, how many more positive charges do I have than negative charges? If I have one positive charge, a proton, and one negative charge, an electron, then my total charge is what? It's 0. If I have 2 protons and 2 electrons, then my total charge is still 0. So if I have a net charge, it means I have more of one than the other. So let's say I have a total charge of 1 coulomb. That tells me nothing about how many total charges I have. I could have any number of protons and electrons, but if I have the same number of each, then my total charge is 0. That tells me how many excess of 1 I have. So if it's plus 1 Coulomb, that means I have more positive charges than negative charges, and it means I have n charges of 1.6 10 to the minus 19 coulombs per charge, and so n is equal to, means I have 6.25 times 10 to the 18th charges. That's actually incorrect. It's 6.25 times 10 to the 18th excess positive charges, more positive charges than negative charges.
So remember that Newton's law of gravitation tells you that the force between two massive bodies is proportional to each mass and inversely proportional to their distance, the distance separating them. And the constant of proportionality is capital letter G, the gravitational constant, and this is a radial force. So in exactly the same way as Newton's law of gravitation works for two masses, Coulomb's law is the electric force law. It tells us the electric force between any two charges. And Coulomb's law, in the exact same way as Newton's law, tells us that the force is proportional to each charge and inversely proportional to their distance squared. Nothing new there. And the constant of proportionality here is just, it doesn't have a fun name like gravitational constant. It's just K. Doesn't have a name. That's the constant of proportionality, and it is also a radial force. Now we got to be careful because Newton's law is an attractive force in the radial direction, and Coulomb's law is a repulsive force in the radial direction. In other words, two masses, m1 and m2, regardless of their charges, have a gravitational force such that m1 attracts m2, right? This is F1 on 2, it's radially towards, and m2 attracts m1, this is F2 on 1. Whereas with two charged objects, if I have two charged objects, let's say two tennis balls with charge, I don't know, I guess tennis balls can get charged, and if they are positive charges, then it's going to be a repulsive force. And look at Coulomb's law. Coulomb's law, Q1 and Q2, if they're both positive, then we didn't say, but K is a positive constant. If Q1 and Q2 are positive, then we get a positive number. This ends up being positive. So let's just start with two positive charges. And if there's two positive charges, it's repulsive. In other words, if the value of Coulomb's law is positive, then that's a repulsive force. But if one of these charges is negative, then it's an attractive force, right? But what happens there is if one of the charges is negative, let's say we put in a plus 1, whatever units for this one, and a minus 1, whatever units for that one, then we get negative r hat. And that tells you it's negative of repulsive and it's attractive. So if this is a positive charge and this is a negative charge, then they're going to attract each other like two masses do. And then if it's two negative charges, you should be able to see that a negative times a negative is a positive, so it's repulsive. So Coulomb's law says that two positive charges, Coulomb's law is a repulsive force. Or I should say, if Coulomb's law is positive, that means it's a repulsive force. Whereas if Newton's law of gravitation is positive, it is always positive, and it's an attractive force. If Coulomb's law is negative, then it's negative or repulsive, and it's attractive.
So I've written here Coulomb's law, which is the electric force between two point charges. And we said that it's proportional to the values of the point charges divided by their distance squared, and it's in the r hat direction. That's indicated in the picture. If I have 2 point charges and I want to know what the force that Q1 exerts on Q2, Q1 exerts on Q2, then the force is if they're both positive, the force is repulsive, right? So the force is away, and it's in the radial direction away from Q1, hence the radial direction between two positive charges. If they're two negative charges, the negatives cancel and it's still radially away. And if they're positive and negative, then it's the minus radial direction and it's an attractive force. But it's still the same kind of force, the same structure as the gravitational force. The constant K, remember the constant G in the gravitational force, GMM over R squared. G was the universal gravitational constant. The constant K here is often also written as, and we'll learn more about this later, 1 over 4 pi epsilon 0, where epsilon 0 is called the permittivity constant. So again, K is just a proportionality constant, but some other physics can show us that we can write K, again, 1 over 4 pi epsilon 0. We can write K in terms of this thing called the permittivity constant. Now actually, with a sub-zero on it, we usually mean that's the permittivity of free space. Epsilon 0 is the permittivity of free space. That's what the 0 refers to. Permittivity of free space. In other words, of vacuum. Whereas epsilon is the general permittivity. What epsilon is a measure of, it's a measure of how big electric forces are in certain materials. So since we're talking about these two charges are just in free space, then we use epsilon 0, the permittivity of free space. But let's say that the charges were embedded in some other material like wood or metal or glass or something, then the electric force would be somewhat mediated by the properties of the material they're embedded in. And so we would just have K as 1 over 4 pi epsilon, and epsilon would be the permittivity of that particular material. We will mostly be talking about charges in free space, so we're not too worried about permittivity of materials yet. That'll come up later on when we talk about capacitance and we're putting materials between capacitor plates, but for now we're just talking about free space. So the value of K for free space is 9 times 10 to the 9th, whatever units, it's MKS units, and so that's going to be meters squared per Coulomb squared Newton meters squared per Coulomb squared. And that also tells us that epsilon 0, the permittivity of free space, is 8.85 times 10 to the minus 12, whatever units. That should be the inverse, so it's going to be Coulomb squared per Newton meter squared. So let's just look at the magnitude of this electric force for a second. I think I said it earlier, but there's no reason you should necessarily know this, but a Coulomb is actually a lot of charge. To get an excess charge of a Coulomb is pretty hard to do because these charges push against each other. If you've got a lot of protons together, a lot of electrons together, they push against each other pretty hard and they don't want to be together. That's why neutral is preferred. So just take it at my word that a Coulomb of charge is a fairly large amount of charge. And you typically won't find a Coulomb of a net charge of a Coulomb on something. And if you do, you don't want to touch it because you'll get a nice shock. But let's just take two tennis balls. Maybe something slightly larger than a tennis ball. Because let's just, for simplicity's sake, let's say that they're 1 kilogram each. And let's take these two masses, two large tennis balls, two strong person tennis balls, and let's separate them by 1 meter. Let's put 1 Coulomb of charge on each of these tennis balls. Let's put a positive 1 Coulomb of charge on each of these tennis balls. And let's ask, what is the gravitational force, the magnitude of the gravitational force between these two tennis balls? It's an attractive force, and the magnitude of that gravitational force is G(m)(m) over R squared. That's whatever G is. And so when you plug in the numbers, everything are ones except for the gravitational constant, so you get 6.67 times 10 to the minus 11 newtons. Let's look at the electric force between these two objects. What is the electric force between these two objects? KQQ over r squared, 9 times 10 to the ninth, 1 over 1 squared, newtons. So which one of these forces is bigger? Well, I think it's pretty evident from the numbers that I gave you that the electric force is significantly larger than the gravitational force. Actually, the gravitational force would be negligible, would be immeasurable compared to the electric force. These two are going to be attracted by a gravitational force of 6.67 times 10 to the minus 11 newtons, but they're going to be repulsed by an electric force of 9 times 10 to the ninth newtons. What's important to take away here is, sure, we could put zero charge on these two objects and then the gravitational force would be bigger than the electric force, but generally, electric forces are much larger than gravitational forces. So, for instance, when you take two fundamental charges, two electrons, and you put those 1 meter apart, their electric force of repulsion is always going to be much greater than their gravitational force of attraction. The electric force is a much larger force than the force of attraction. Okay, to finish up our discussion of the Coulomb force law, or the electric force between 2-point charges, let's go ahead and just do a couple of problems. We're not going to do a lot with this because this is identical, as I've said over and over again, to the gravitational force law, and so there's nothing new here. We just got to add two vectors add vectors when we're talking about the force the force between multiple charges. So what we do want to look at is collections of charges and how we calculate the forces between collections of charges, but we just did that with gravitation. So the force between two charges, easy enough, it's a scalar thing. But the force between three charges, we had to add the two forces as vectors. Force between a continuous charge, we had to integrate. Force of a ring, force of a shell, and force of a sphere. So we do the exact same thing with electricity, but it's exactly the same. There's nothing new, so there's nothing more that needs to be done, except that I'll just do a couple of quick examples. So foreshadowing, then we just want to make sure we understand Newton's shell theorem and how it applies here, and then we're going to move on to the concept of the electric field. We talked about the gravitational field before, and now we're going to move, once we've done a few examples, to the electric field. So in honor of the Super Bowl, I'm going to ask you about the matchstick trick, which I'm sure some of you have seen before. But every time I see this, I always get puzzled over it. I can never remember how to do it. The idea is that you have 4 matchsticks indicated here by the things that are matchstick-like looking. And they make a goalpost, and the thing inside that goalpost is not a slug, but is meant to be a football inside the goalpost. And the idea is can you move exactly 2 matchsticks, Can you move exactly 2 matchsticks to get the football outside of the goalpost, but to still have a goalpost? Can you move exactly 2 matchsticks to get outside of the goalpost? And this often puzzles me. For some reason I have trouble seeing it, but it really is. There's no trick to it. You move 2 matchsticks and you make a goalpost that doesn't have the football in it if the football stays in the same place. So I'll give you a second to think about that. Actually, I don't need to give you any time to think about that. If you want to see the answer, just let this go. Otherwise, hit pause and see if you can figure it out yourself. So the answer, when you see it, really seems quite straightforward to me anyway. So you're going to take this matchstick and you're just going to move it over half a matchstick's length, and you're going to take this matchstick and you're going to go ahead and put it down here. So in the end, what you have is this matchstick, which is moved over to here, and this matchstick, which is moved down to here. And now we have got, let's go ahead and erase the matchsticks that we just got rid of. And now we've got a goalpost without a football in it. Ta-da. So let's go ahead and do this Coulomb's law problem. We have 3 charges fixed in place on a coordinate axis, and charges Q1 and Q2 are on the y-axis, equally distributed around the x-axis, and charge Q3 is along the x-axis. I give the values of the charges. Q1 is plus 1 microcoulombs, Q2 is minus 1 microcoulombs, and Q3 is plus 2 microcoulombs. And I've added some distances so that Q1 and Q2 are separated by 6 meters, and Q3 is 4 meters along the axis. So what we want to know is what is the net force on Q3 due to Q1 and Q2, due to the electric force of Q1 and Q2. So the first thing we want to do is we want to draw in the force of Q1 on Q3. Q1 and Q3 are both positive charges, so we'll draw in the radius vector. This is the radius vector, and the force is therefore, is repulsive. It's supposed to be along the same line. The force between Q2 and Q3, this is the radius vector, but they are opposite charges, so it's attractive. So the force is opposite the radius vector in that direction. I didn't draw these terribly well because there's symmetry, so I tried to erase and redraw them a little bit. But in any case, it is a symmetrical situation where the two forces actually create an equilateral triangle. I'll draw it a little better on the next page. Oh, no, I'll just redraw it here. So the two forces have some symmetry, and you can see that the x component of Q1 on Q3 points to the right. The x component of Q2 on Q3 points to the left. And because the magnitudes of these two forces are going to be the same, look at the Coulomb's force law, the magnitudes are going to be the same, then the x components cancel. Whereas the y component of Q1 on Q3 points downwards, and the x and the y component of Q2 on Q3 points downwards, and so those two will add. So all that's left when we do the math, when we write down the two vectors and break them into components, is the y components add and the x components cancel. So all we really need are the y components. The magnitude of each of these forces, the electric force in magnitude is k q1 q3 over r squared, or k q2 q3 over r squared. They each have the same magnitude, which we can even put in the numbers. 9 times 10 to the 9th times 1 microcoulomb, that's for Q1, times 2 microcoulombs, that's for Q3, divided by their distance squared. Do the geometry, right? That 4 meters was the distance of the x-axis, 3 meters was distance along the y-axis. So the hypotenuse is actually 5 meters. I chose a 3, 4, 5 triangle. So we've got 5 meters squared. That's the magnitude of Q1 on Q3. The magnitude of Q2 on Q3 is going to be the same. The only thing that's different is there's going to be a negative 1 microcoulomb, right where that green arrow is. But the magnitude of the second force of Q2 on Q3 is still the same. There's just going to be a minus sign, which is what gives us that direction towards Q2. Let's go ahead and find the y component of the magnitude of the force. And so in order to find the y component, we need to find this angle right here, that angle right there, which I'm going to call theta. Now notice that I've just chosen that angle so that the y component is going to be f cosine theta. Don't be confused by often y components are f sine theta. I've chosen that angle so that the y component, the force that's pointing in the downward direction, has the the relationship to the force vector of f cosine theta. So Fy is equal to f cosine theta. If you chose the other angle in that triangle, then yes, Fy would be f sine theta. So how do I know what that angle is? We need to look back at the original diagram. Look above at the original diagram. This here is theta that I'm indicating in the diagram. That's theta. And that angle is the same as this one here. That's theta, theta, theta. So therefore, from the original diagram, we can see that the tangent of theta is opposite over adjacent 4/3. And so from that, we can figure out what the cosine of theta is. And then we can figure out what the y component is. And remember, we're adding the two y components, which turn out to be the same because of the numbers that I chose. So the net force, which is in the downward direction, where those two vectors are parallel to each other, is going to be adding the y component of q1 on q3 plus the y component of q2 on q3. They're the same, so it's just going to be 2 times one of the y components. So plugging in for the angle, I get cosine theta is 0.6, and therefore we can plug in the numbers, and I get f net, plugging in the 0.6 to the for the cosine theta. I get 0.86 times 10 to the minus 3 newtons. And the direction is, if we choose standard directions on the previous page, then it's going to be the minus y hat direction. It's in the downward direction.